using the connection between the nth order polarization and the dipole operator expectation value. I guess we have to put the times n in here, which I forgot. Now what we can do is we have an expression for this. We wrote it out last time. We simply have to write down what this scalar product is. All right, so we're going to do that. We'll be more careful when we write down rho in our equation. We'll use the correct Liouville space Dirac notation. All right, so what we end up with is this. All right, so we end up, we have the I over h bar to the n part out front, of course, the integrals. All right, and then we have our expectation value stuff. We can put n in here wherever we want. The n is not the most important thing. Okay, so we have the v. We have the g, which is all the sums of all these times. We have all the v's. All right, so remember how this goes is Tn minus 1 plus Tn minus 2 all the way down to V T1, V of 0, and rho EQ. And then we explicitly write down that this is this Liouville space density. And then we have the fields. We don't need to write them all out every single time. Okay, so what we do now is we recognize that this G is operating, can be thought of as operating on the V to the left, right? And since it can operate on the V to the left, what that's going to do is it's going to shift the V to this time, whatever that time is. All right, and so the way we do that, now what I'm going to do is I'm going to write out, we're going to work just on this part here. Let's just take that part. So I might abbreviate it like ... this part here. When we shift V by this amount, we'll have V Tn plus Tn minus 1 right? And then we'll have all the V's inside. And what our job is, what we're going to be doing, as you might guess, we've already gotten back our sort of ourselves more or less to a Hilbert space looking operator here. Of course, it's in a vector, so that's because it's in Liouville space, but we're going to switch back at the end into Hilbert space. Liouville space in some sense was like a intermediate space to help us work through this derivation. Okay, so what's next here? We can write down a little bit of the notation separately. So remember that we have each of these terms here, like V of T1. V of T1 came from doing G T1, V, the thing that doesn't depend on time, T1. Okay, and remember what these G's are. The G's are nothing other than the time evolution operator and with the Heaviside function on it. So G, what's G again? G of tau, for example, is Heaviside function of tau. So when this is greater than 0, times e to the minus I over h bar times L times tau. Okay, and the L was the L naught. This particular G is the L with L naught. Okay, so the point is that what we can do is we can put this back in. So we'll have theta T1 E to the plus I over h bar L0 T1 V times theta T1 minus I over h bar L0 T1. All right, so the theta is one of those weird functions, right? If you square it, it's exactly the same. If you square the function, it just looks exactly like the same, and it's just between 0 and 1. So this is actually the same thing as just theta T1 dot dot dot. And what is this? Well, this is just the ordinary interaction picture version of V. So this is actually V of T1. All right, so what you can do if you do this to all the terms, this one, this one, this one, this one, this one, you can see each time you're going to end up with another theta. All right, now I picked a convenient one here where I had them only one time point in there. If I was looking for a harder case, I would have it be like T1 plus T2 for one of the other time points. All right, so the goal here is we want to basically take these Heaviside functions and shift them over while we have the V's alone. All right, well, you know what's going to happen to the V's. We're going to get V of T1, V of T1 plus T2, and so on. We need to know what to do with these Heaviside functions that are going to pop out as we keep going, right? So the next one to the left is going to be theta T1 plus T2 times theta T1. That's the one that we already have. And we want to figure out how can we write this in a simplified way. So the first hint of what to do here is to remember what these Tn's are. Right? We define the Tn's as time intervals. For example, literally Tn is T minus tau n. Right? And this is all in this time-ordered operator. That means that we know that T is greater than tau n. So we know that Tn is greater than 0. In fact, we know all the T intervals are positive in terms of time. Okay, so what that means is, what we're asking here is what happens when we combine these two. So remember, a Heaviside function is going to be 1 when T1, for example, in this case, plus T2, that sum is greater than 0. That's what a Heaviside function is. So we have the condition where T1 plus T2 is greater than 0. All right, now what do we know about the sign of T1 and T2? Both of them are greater than 0. Okay, so if we know that the inside of this is greater than 0, or we want it to be greater than 0, right? Then we know that the T1 plus T2 theta is equivalent to saying, are both T1 and T2 greater than 0, which we can write by writing T1 times T2. And this isn't going to work if they could have negative signs, but they can't. So then what you have here is you have theta T2, and then you have theta T1, and you already had a theta T1 before. And what we said before about Heaviside functions equaling themselves squared, this is equal to theta T1. So overall, this is equal to theta T2 theta of T1. All right, so that simplification allows us to rewrite this whole business here with this sort of expectation value, okay, in the following way. So we have V. The V part's not going to change. So let's just put that like this. All right, the script V's are actually going to be the same script V's, but we're going to pull out the theta parts. So we're going to have V Tn minus 1 dot dot dot. And I'll just skip all the way to 0. And then we have theta, and then it's the product of all the thetas. So theta T1, theta T2, the order doesn't matter, up to theta Tn. Okay, that is this chunk, that's this chunk. And now we have the key definition. So the key definition is S n of Tn minus 1, T1, we call that equals, and we're going to collect a couple of the terms that are outside. So it's equal to 1 over I over h bar to the n times this expectation value. So we're going to have the thetas and then we have V. Okay, so this function here, S, is what we are going to define as the optical response function. Now you might think it's still in a ridiculously opaque form, which I agree it is. So what we're going to do is simply switch ourselves back to Hilbert space, and what you will find out, amazingly enough, is that the form of this gets much simpler, in a sense. In the sense that you'll see things that you recognize more than these peculiar Liouville space matrix elements. It's going to turn it into a bunch of nested commutators, and I warned you that that was coming. Now, I should say, on the one hand, it will turn it into something that looks more familiar, and on the other hand, it makes it into something that is incredibly difficult to calculate. So having all the nested commutators is essentially what makes calculating nonlinear response or nonlinear signals so difficult for our theoretical friends. But nevertheless, they know what their job is, and they can either do it or not. And there's obviously a few approximations you can make about different kinds of factorizations, and we'll talk about those as we go. Okay, so this is it. We're going to do the great re-Hilberting after this board is erased.